All right, today we're talking about Chapter 2, Section 2, more on functions and their graphs. So we're going to talk about how we identify functions and the different names we have for them in this section. Just one moment. My pen's not working right. Okay. Alrighty, so let's see. The first thing we're going to talk about is increasing, decreasing, and constant functions. So an increasing function, well, let's just snip this real fast and then talk about it. All right. So as you know, we read these graphs from left to right. So by reading from left to right here, all right, if we are going up, all right, again, reading from left to right, if we're going up, then we are increasing. If we are going down, then we are decreasing. Again, reading from left to right. And of course, if we are flat, we are constant. Now up here we have the more rigorous mathematical definitions. Uh, these are obviously precise definitions and definitions that I wouldn't hurt you, I guess, to have them memorized. But really, they're used a lot more for pure mathematics and proofs. But these are the definitions of an increasing, decreasing, or constant function. We also have an undefined. I don't know if we're going to touch on that. Doesn't look like it. Okay, so let's look at example one. So example one reads, state the intervals on which each given function is increasing, decreasing, or constant. Okay, so we're going to look at 1a here, and if we're going to try to not try to, but talk about where we're increasing and where we're decreasing, then we're going to start with, oh no, a pen. Oh, there we go. Okay. All right. So as we look at this graph, we see that it's going down, 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 all the way. Like again, this arrow means we're going up all the way to infinity, right? So from negative infinity to 0, it looks like we are decreasing. Okay, so we're going to say that we are decreasing. We'll put a D for decreasing. We're decreasing from negative infinity to 0. Now we're going to put a parentheses around 0 because at exactly 0, we're neither increasing or decreasing. Okay, so we're putting parentheses there. All right, and then we will also be increasing from, it looks like, from 0 all the way to, looks like about 2, right? So from 0 to 2, we are increasing. And again, we're going to put a parentheses. And then looks like we are decreasing again from, looks like from 2 to positive infinity. Okay. Now, there's no constant. We're not constant anywhere in this graph, but it looks like for B we are. So looking at B, it looks like we're constant from negative infinity all the way to a positive 2. Okay. Uh, so, well, I'm sorry, not positive, to a 0. We're only doing the x's. So it looks like we are constant. We'll be constant here from a negative infinity all the way to 0. All right, so I'm having a little bit of trouble with my pen today. I don't know why. These batteries are pretty new. Maybe they're cold. Uh, anyways, that's where we're constant, and it looks like we are going to be increasing. So we're increasing from, looks like from 0 to infinity. All right, and that's increasing, decreasing, and constant. All right, next we're going to talk about relative minimum and relative maximum. And these concepts are aptly named, so they're not too confusing. So if we talk about a relative maximum, then we're talking about a point on the graph that is, relatively the top, relatively the maximum of whatever I'm looking at. And then, of course, we have a relative minimum, which is, again, a minimum relative to what you are looking at. So uh, that's the idea of relative minimum and relative maximum. And symmetries. So next we're going to talk about symmetries. And we're going to go ahead and just snip this and put it on the same page here. All right, so a symmetry, right? Symmetry is basically a mirroring of what you're looking at, right? So if you're symmetric about, or well, yeah, let's keep this in math terms. So if we're looking at this graph here, right, graph being these lines, we see that these lines, they are symmetric about the y-axis, right? So we can see the mirror from one side and a mirror on the other side. We are symmetric about the y-axis. Here it appears that we are symmetric about the x-axis. Okay, so when we're symmetric about the x-axis, we can mirror our graph across the x-axis and be done with it. Next up, this doesn't really, I mean, it's not symmetric about the y-axis or symmetric about the x-axis, right? But it does have a symmetry, and its symmetry, we say that it is symmetric about the origin, okay, or about the center here. And it's basically just taking the graph, flipping it across the y-axis. So let's show you what that looks like. Flipping it across the y-axis, and that's not good at all, but hopefully you understand. All right, flip across the y-axis, and then flip it across the x-axis. All right, and that's symmetry about the origin. Now it's obviously really easy to tell um, when you're looking at a graph, what's the symmetry. But let's see, I guess we'll snip this. But it's not as easy when you do things algebraically, right? Right? Whenever you have equations. So the way you test for symmetry with equations. So the graph of the equation is symmetric with respect to the y-axis. For every point xy on the graph, there's a point negative y, x positive y on the graph. Again, that's just a coordinate on the other side, with the symmetry. And the way you do this is you substitute negative x for x in the equation, and it results in an equivalent equation. Okay. Well, if we want to test for symmetry with respect to the x-axis, we substitute a negative y into the equation, and if we have an equivalent equation. And then if we want to test for symmetric about the origin, we substitute negative x for x and negative y for y in the equation. And if we get a resulting, if we get the same equation, then we are symmetric about the origin. Now, that's, again, pretty darn confusing, but let's actually do an example, and maybe it'll clear it up a little bit. Okay, so what we're going to have to do here is we're going to have to substitute in a negative x, a negative y, and then a negative x and a negative y. Okay, because we want to test for all the different symmetries. Alrighty, so let's go ahead and test for symmetric about the y-axis real quick. So in order to do that, we're going to have to substitute in a negative x for a positive x. So let's say let's make this a y-axis test. Let's see how. Really want to be a little bit precise here. So yeah, we'll just put y-axis test and then do underneath. Y-axis test. Okay. All right. So if I'm trying to find out if we are symmetric about the y-axis, then we substitute in a negative x. So let's go ahead and substitute a negative x in. So we're going to have a negative x is equal to y squared minus 1. All right. Well, by doing that, and then we're going to multiply both sides by negative 1 and solve for x. So if we do this, we end up with x is equal to, this way we're going to have a negative y squared and then plus 1. Okay. All right, and looking at this, this equation here is obviously not the same as the original equation. My original equation being x equals to y squared minus 1. Okay, and since it is not the exact same equation, right, then this is not going to be symmetric about the y-axis. Okay, so now let's try the symmetric about the x-axis. So let's write x-axis test. So this time we're going to be replacing y with a negative y. So we're going to have x is equal to, and then a negative y squared minus 1, right? And then doing the arithmetic here, right, we get x is equal to, which is simply y squared minus 1, okay? So looking at this particular graph, is this the same as this? All right, well, yes, it is. X equals y squared minus 1. So it is the exact same. So we are indeed symmetric about the x-axis for this particular graph. Right? And then lastly, we're going to do origin test. And the origin test is replacing both x and y with a negative x and a negative y. Okay, so we're going to have a negative x is equal to a negative y squared. Oh, sorry, didn't mean to put that inside. There we go. Minus 1, and of course we can see that this is not going to work out. We're going to have a negative x is equal to y squared minus 1, and of course if we solve, we multiply negative 1 by both sides, we get x is equal to a negative y squared plus 1, and of course this equation is not the same as my original equation, so we say that we are not symmetric about the origin. All right, so next up we're going to talk about even and odd functions. So even and odd functions, they are basically this. We're still talking about symmetry. Okay, so let's go ahead and snip this and we'll expand on it. Alrighty, so an even and odd function, looking up here, we have seen that a graph is symmetric with respect to the x-axis. It usually fails the vertical line test, right? Because I mean, if we are symmetric about the x-axis, then it's not going to be a function by definition, right? Because we have to be able to pass that vertical line test. All right. So, however, many functions have graphs that are symmetric with respect to the y-axis or the origin. So we give these functions special names. So an even function is a function that is symmetric about the y-axis. So back here when we did all this, we basically, y-axis test, x-axis test, and origin test. Okay. Well, right now, what we're saying here is that if you're symmetric about the y-axis, we're going to call that an even function. If you're symmetric about the origin, we're going to call that an odd function. If you're symmetric about the x-axis, then you're not a function at all, right? So let me go ahead and kind of show that real quick before we move on. We have some graph like this, and I didn't mean to put a little indentation there, but all right. This graph, for my best attempt here, is symmetric about the x-axis. But notice how it does not pass the vertical line test, and therefore it is not a function, right? So again, we're talking about functions. So we're only concerned with functions that are symmetric about the y-axis. I guess we can do it like this. That are only symmetric about the y-axis, or that are only symmetric about the origin. Okay, the symmetry there. And if we're symmetric about the y-axis, we call that an even function. And if we're symmetric about the origin, we call that an odd function. So I want you to look here and these blue areas here. So notice, I mean, before you even look at the words, without even looking at the words, notice how in both cases it looks like we are taking f of negative x. Okay, and that will be the case. We're going to take, excuse me, we're going to take we're going to evaluate the function at negative x in both cases. All right. Well, by doing that, if we get the original function back, similar to how we did here, if we get the original equation. If we get the original function back, then we have an even function. If we get the negative of the function, then we have an odd function. Okay. So let's go ahead and do an example like with that. Well, looks like we're before we do the algebra of it, looks like we're going to do an easy problem here. Okay. And of course we can just kind of look at this and tell, right? So looking at a, right? We see that it is not symmetric about the y-axis, right? Because if it were, then this little hump here would have a mirror over here, right? And it doesn't. But it's symmetric about the origin because we can say, okay, well, we have this little bump here. If we reflect it across the y-axis and then the x-axis, we complete the graph. Right. So this particular function we're going to say is an odd function. Okay. Well, b. All right. Well, b look is I think is very obvious that it is symmetric about the y-axis, right? So if it's symmetric about the y-axis, we call that an even function. And then lastly, we see that this graph, it's not symmetric about the y-axis and it's certainly not symmetric about the origin. So therefore, we would say that this is neither. Okay. Okay, so next up we're going to do the even and odd function here. Let me make sure that it was just these three. Yeah, okay. Alrighty, so example 5 reads, determine whether each of the following functions is even, odd, or neither. Then determine whether the function's graph is symmetric with respect to the y-axis, the origin, or neither. Okay, so in order to do this, uh, we're going to replace x with a negative x, and then we're just going to do the arithmetic. Okay, so starting with a, we're going to replace the x with a negative x. So we're going to say f of negative x. Right, and so I'm replacing the x. So we're going to say negative x cubed. Oh, here we go. Oh, that worked out good. Minus 6 times a negative x. Let's do the arithmetic here. Well, negative x cubed is just going to be negative x cubed. And then we have a minus 6 times a negative x. So we're going to have a plus 6x. Alrighty, so looking at this equation, is it the exact same as this equation? All right, well, we look at it. It looks like, well, when we have a negative x and then we have a plus 6, whereas the original equation has a positive x and a minus 6. Okay, so it's not the exact same. Alrighty. Is it the exact negative? Is it the exact opposite? Right, well, we have a negative x and a positive 6, and in our equation we have a positive x and negative 6. Okay, so it is the exact opposite of it. So therefore, we would say that this particular function is odd. It is an odd function. And of course, it wants us to state whether the function is symmetric with respect to the y-axis, origin, or neither. Well, if it is an odd function, then it's going to be symmetric with respect to the origin. So we'll put sim origin the best we can. Okay. Next up, we have b. So we're going to say f of negative x. Again, every single one of them start like this. So f of negative x, and then we're just going to plug in negative x. So we're going to have a negative x raised to the 4th power minus 2 times a negative x squared. Okay, well, what is negative x to the 4th power? Well, that's negative x times negative x times negative x times negative x. So it's going to be a positive, right? So it's going to be an x to the 4th. And then we have a negative x quantity squared, so it's going to be a positive x squared. So we're going to end up with a negative 2 times a positive x squared, so minus 2x squared. So same thing. Is this the exact same as this? Well, yeah, sure is. It's the exact same, so therefore we're going to say that this is an even function. Okay, so we say this is even, and it is symmetric y-axis. And I bet the last one's going to be neither, just because that's always how it works out, right? So we're going to say f of negative x, all right, and then we're going to plug in negative x here, so negative x squared plus 2 times a negative x plus 1. Doing the arithmetic here, we have x squared and then minus 2x plus 1. So looking at the problem, is it the exact same? No, because I have a negative 2x down here and a positive 2x in my original equation. Is it the exact negative? No, it's not, because the x squared and 1 are both the same. So it is neither even nor odd. Okay, so that we would say that it is neither. And there is, well, neither, right? There we go. All right, so piecewise functions. Piecewise functions are functions that, if you read my bio, when I took math classes, these kind of math classes in undergrad, I was not going into mathematics, and because of that, I would come across equations like or problems like this, piecewise functions, and I would just be like, well, I really hope there's not going to be a lot of these on the test because I don't feel like learning it. All right, I was very lazy. I was a horrible student. Obviously, I turned things around, but my point is this: these problems are a lot easier than you think they are. Okay, so what I mean by that is, well, you just have to put in the time and you'll understand it. So how do we understand this? Well, looking at the example, we've got uh, we've got our function name is c. It is c of g, and it's got two. It's essentially kind of two separate equations. So you know how whenever you might have taken a test or something, and it's supposed to be a 10-question test, but each one of the questions has like 3 parts, right? So it's for like a 30-question test. Well, piecewise functions are kind of like that. They cheat, all right? They are one function, but they are multiple functions. And these functions are basically just split off into these lines. So this is one function, and this is the second function. And all you have to do is just determine what you're looking at. Determine which function uh, is the one we're going to be evaluating at. So looking at A, we see that it is C of 10. Oh, that's not the eraser. Right. We see that we're wanting C of 10. So this number here inside this 10, all right? What I'm going to do is I'm going to look at my domains here. Okay. So which one of these two does 10 fit in? Is it between 0 and 15, or is it greater than 15? Well, obviously it's between 0 and 15, right? So I'm going to look at my first equation, which is 40. So my answer is just simply going to be 40, right? So we're going to say C of 10 is just equal to 40. And that's it. Now, I think there's some ambiguity there, and so B is really going to drive the point home. So let's look at B. So B, we're looking at C. Man, I keep on messing that up. We're looking at C of 45. Okay, well, again, is 45 between 0 and 15? No. Is it greater than 15? Yes. So I'm going to use this equation here. Now, this equation actually has a variable in there that I can substitute in. All right, so for A there wasn't a variable, but for B there is. So I'm going to use the second equation. The second equation is let's actually do this like this. We're going to do C of 45, and the second equation is 40 plus 0.60, and let's fix that 0, and it's G minus 15. Okay, well, but we are choosing the G to be 45. Okay, so we're going to erase the G here, and we're going to make it a 45. And then we do the arithmetic, and we solve the problem. Okay, well, we've got 40 plus 0.6. And what is 45 minus 15? Well, that's going to be 30. So times 30. All right. And what is 60% of 30? From 5, so 20. So we're going to say 40 plus 20, or in other words, 60. So 60 is my solution to this problem. No, that's not right. I'm sorry. It's not 20. It's 18. 6 goes into 35 times, not 5. So plus 18. So the answer is 58. Okay. So again, that's piecewise functions. Um, like I said, when I was taking math, I just like, oh, no, not even dealing with piecewise functions. In one ear, out the other. But just to kind of recap, again, depending on where you're evaluating at. So we have the numbers 10 and 45. You're going to look at these domains to see which one you fit in, right? So if we had C of 3, C of 3, okay? Well, is 3 between 0 and 15? Yeah. So then you would just say, well, the answer is 40. That's it. Okay. And the second equation is a little bit, there's more arithmetic involved because we had to plug a number in. But if we chose, C of 20, well, we would just do, 20 minus 15, which is 5 times 0.6, and then do the arithmetic that way. But please don't be like me. Piecewise functions are a lot easier than younger Sherman knew. So, all right. Lastly, we're going to talk about the difference quotients. Now, the difference quotient, uh, we use it a lot when we talk about rates of change. Up until now, a lot of our equations have been linear equations. So linear equations are pretty easy to see, essentially the rate of change because, well, I mean, it's one thing. It just moves, right? The slope. But if we have equations like, let me just draw this. Okay, so if we have just some linear equation like this, it's easy to tell a slope, isn't it, right? I mean, we do the whole rise over run, and where to figure out the slope. Okay, but what if we have an equation like this, something like that? Well, it's a little bit harder to find the rate of change, right? In fact, we have to find the rate of change at a point. We can't really necessarily find the rate of change of the entire function. So with that said, we use the difference quotient. Now this kind of leads into calculus, but we're not going to get too far into it, obviously, in this course. But just kind of give you a little, I wouldn't necessarily even a heads up, more of a teaser. Okay. Unfortunately, it does get pretty wonky though. So let's just begin. Um, so the definition of difference quotient of a function is f of x plus h minus f of x divided by h. For h not equal 0 is called the difference quotient of a function. Right. So what we're going to do is we're going to find the difference quotient here, and which is I won't necessarily say funny, but the cool thing is whenever you do get to calculus, you can look at an equation like this and find the derivative of it without even having to do all this. I mean, you can look at this equation right here and just be like, oh, okay, the derivative of that is 4x minus 2 or minus 1. But that's it. But anyways, let's begin. So the first thing we want to do is we want to find f of x plus h. So before we even jump into the difference quotient, we're just going to find f of x plus h. So in order to do that, we're just going to plug in an x plus h everywhere where you see an x in the equation. So we're going to say, I don't know, we'll make this 2-pager. Probably gonna have to be a 2-pager anyways. But so f of x plus h, that is going to be, I'm just gonna start it down here because it's gonna be pretty long. So 2 and then x plus h quantity squared minus x plus h and then plus 3. And then if we do the arithmetic here, we're going to have to expand this, so it's going to end up being x squared plus 2 xh plus h squared, and then we're going to distribute that negative sign through, so minus x minus h plus 3. Let's put the parenthesis there. All right, and then it looks like we can distribute the 2, so we're going to distribute the 2 through, and we're going to have 2x squared plus 4xh plus 2h squared minus x minus h plus 3. Let's fix that h. Glad my pen decides to just, quit in the middle of a letter there. Okay. And is there any sort of, well, there are no like terms. Okay, so that's that. Alrighty. So that is f of x plus h. So that's A. Now, B is wanting us to find the difference quotient. So notice how difference quotient is f of x plus h minus f of x, right? And then divided by h. Well, we already found f of x plus h. Okay, so I mean, realistically, we already found the hard part, right? So what I'm going to do without, I don't, yeah, let's actually let me snip this and just put on the next page. Just well, luckily I made this super crooked, so I think that'll do. Okay, so again, this is f of x plus h. Okay, so to finish out the equation, I'm going to have to do minus f of x. So we're going to subtract f of x. So minus f of x is going to be, what was f of x? F of x is this, 2x squared minus x plus 3. So minus 2x squared, I don't forgot, minus x plus 3. Minus x plus 3. Okay, well, without having to rewrite the problem, what I'm going to do is I'm just going to go ahead and drop the parentheses and then change the sign of everything. Okay, so I'm going to drop the parentheses, and then I'm going to change the sign. So this is going to turn into a positive 3. This is going to turn into a negative 3. Right. And then of course, that minus sign is going to stay there because it was minus the f of x, and the 2x squared was a positive. So I'm just going to keep that negative sign there. And then it was all this over h. All right, so now you can see how it gets a little hairy, right? Well, what I'm going to have to do is I'm going to have to combine like terms, and we'll simplify. So let's look at this. So we have the 2x squared. Well, that cancels with this, right? The minus 2x squared. Looks like we have a negative x and a positive x. They cancel. We have a positive 3 and negative 3. They cancel. And that looks like it's all the canceling there. So I can rewrite this equation now as 4xh plus 2h squared minus h all over h. Okay, well, I can factor an h out of the numerator, so I can factor an h out of the numerator. So I'll have a 4x plus 2h minus 1, and then that's all over h. And then I can cancel my h here, and so my solution is just going to be 4x plus 2h minus 1. And that's the difference quotient. So I think that's it. That concludes today's lecture. Let's make sure I got that right first. 4x plus 2h minus 1. Okay, good. I say it because I know on more than one occasion I've messed that up because it does get long and tedious. But yeah, that does conclude today's lecture.